Hey guys, this is Alex and Meg, and we're going to be discussing section 7.2 on tangents and circles. We'll be giving some definitions, proofs, and examples, and we hope this is helpful. So what exactly is a tangent? There are two theorems that can help us to understand, and those are 7.5 and 7.6. So theorem 7.5 states, if a line is drawn perpendicular to a radius of a circle at the endpoint of the radius, then that line is tangent to the circle. And theorem 7.6 is actually the converse of theorem 7.5. It states, if a line is tangent to a circle at a point P of the circle, then that line is perpendicular to the radius drawn at point P. So now let's just label a diagram so we can get a better idea of what this looks like. Here's a circle, and there's a radius, and remember the tangent is perpendicular to the radius. Also, one other thing is that the tangent will be perpendicular to the radius no matter which radius you draw, because all radii are the same. So how do we know that the tangent is perpendicular to the radius? Also, how do we know that that's true no matter what radius you choose? So let's just do a proof to be sure. So given that AP is tangent to OC at P, prove CP is perpendicular to AP. This is going to be an indirect proof, so we'll start with a statement that contradicts the proof. Either CP is perpendicular to AP or CP is not perpendicular to AP. We will assume that CP is not perpendicular to AP and for our contradiction. So if CP is not perpendicular to AP, then there is another segment, CQ, that is perpendicular to AP with Q on AP. Let R be the point on the ray opposite QP so that QP equals QR. Now triangle CQR is congruent to CQP by SIS, so CR is congruent to CP. Since R's distance from C is the radius of the circle, point R lies on circle C. But then AP has 2 points on the circle and is thus not a tangent. So this contradiction of the given for the problem means that the assumption CP is not perpendicular to AP is incorrect. Therefore, CP is perpendicular to AP. So what would be an example of using theorem 7.5 and 7.6? Let's do a problem. So given AOB is a diameter of circles O, CD is a tangent to the circle at D, CD equals 6 and BC equals 4. Determine the radius of the circle. So the picture that goes along with this problem looks kind of like this, and we can label the drawing as well. What else do we know about this problem? We know that if CD is a tangent, then the radius to the tangent will be perpendicular, right? We also know that both OD and OB are radii, so they will be the same length. So let's call them both x, so now we have a right triangle. And that is a perfect setup to use the Pythagorean theorem. So we can set up the equation x squared plus 6 squared will equal x plus 4 squared. And
so if you work out the problem, you'll get x squared plus 36 equals x squared plus 8x plus 16, and then that is equal to negative 8x equals negative 20. So then you know that x equals 20 over 8. And simplified, that means x equals 5 over 2.
So next up, we're going to talk about theorem 7.7, which states that tangent segments to a circle from the same external point are congruent. So if you draw this out, it makes this look somewhat like an ice cream cone, so we're going to call it the ice cream cone theorem. Alright, so now let's prove 7.7. The given, PT and PQ are tangent segments to a circle C, and we're trying to prove that PT is congruent to PQ, or that the two tangents are congruent. So PT and PQ are tangent segments to circle C, which is given. PT is perpendicular to CT and PQ is perpendicular to CQ because a tangent to a circle is perpendicular to the radius drawn to the point of tangency. Next, angle PTC and angle PQC are both right angles, which is the definition of perpendicular lines. CT is congruent to CQ because all radii of a circle are congruent. CP is congruent to CP because that's reflexive. And triangle CTP is congruent to triangle CQP because of the hypotenuse leg theorem. And finally, PT is congruent to PQ because of CPCTC. Some more definitions. First, inscribed is when a circle is on the inside of the shape. Circumscribed is when the circle is around the shape, or the shape, it's like the shape that surrounds the circle is circumscribed around the circle. Finally, the incenter is the center of the circle inside the shape. A circle is inscribed in the triangles. You're also given that the sides are 3, 5, and 6. So this little segment is called X, and we have to find it. So basically this problem is going to be about chasing sides. So here you have two segments that are both X, and when this whole segment is 3, you know that this little segment right here is going to be 3 minus X, and the one opposite it, this one here, is also going to be 3 minus X using the ice cream cone theorem that we just proved. Since you know that this whole side is 5, then this longer segment right here is going to equal 5 minus 3 minus X, and that simplifies down to 2 plus X. Also, the side opposite that is the whole thing is 6, and the little segment is X, so this segment right here is going to be 6 minus X. Then you also know that since this side and this other side are both tangents using the ice cream cone theorem, they have to be equal. So we're going to set up the equation 2 plus X equals 6 minus X. And when you simplify that down, you get 2x equals 4, and eventually you get x equals 2. Okay, so here's another problem that's a little bit trickier. We're given this figure and told that PT is tangent to circle B and T. PT equals 4K and PA equals 8K. And it says determine the radius of the circle in terms of K. So I know you're already given K as a variable, but you also need to add in another variable for the radius. So you can call it anything you want, but I think it's helpful to call it R. So this length, and this length will all be labeled R, just because they're all radii, and radii are all equal. Then you know this length is perpendicular to the tangent TP because of the theorem 7.5. So what would this length be? So if the whole length PA is 8K, then PB would be 8K minus R. So now we have all the lengths of this perfect right triangle, and we can simply use the Pythagorean theorem to find the length of R. So R squared plus 4K squared equals 8K minus R squared. So then you kind of multiply out R squared plus, and remember it's 4K squared, which equals 16K squared. So R squared plus 16K squared equals 64K squared minus 16KR plus R squared. Then you can subtract, and you eventually end up with 16KR equals 48K squared. You divide each side by 16K, 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 and you end up with R equals 3K. So for the last practice problem, we're going to be doing a word problem. The directions are: a circle is inscribed in a triangle whose sides are 7, 8, and 9. Determine the length of the 6 segments from the vertices to the points of tangency. So let's draw a circle inscribed in a triangle, and these will be the sides. So both of these will be x. Since this entire side is 9, this side right here is going to be 9 minus x, and same with this side here because they're congruent. So you have x, x, 9 minus x, 9 minus x, and then over here, this side is 7, and so when that's x, this side right here is going to be 7 minus x, and the same with this, with its congruent side. So then you end up with 7 minus x plus 9 minus x is going to equal 8. So when you do that out, you have 7 minus x plus 9 minus x equals 8, 7 plus 9 minus 2x equals 8, 16 minus 2x equals 8, 16 equals 8 plus 2x, 8 equals 2x, divide by 2, and you end up with x equals 4. So if x equals 4, then 9 minus x is 5, and 7 minus x is 3. So you end up with sides 3, 4, and 5.